Hello, everyone, and welcome back to KognitoKey. I'm absolutely thrilled to have you here today. We're going to dive right into something that literally happens inside your computer every single day: memory overload. Have you ever actually stopped to wonder how your machine manages to keep running smoothly when we are constantly pushing its memory to the absolute limit? Well, today, we're going to unpack exactly how that magic happens. To really wrap our heads around the problem, let's look at a real-time example. You know the exact moment you boot up a Windows PC? Before you even click a single icon, boom, 50 to 100 background processes instantly start running. Most of the time, they aren't even doing much, just checking for application updates, pinging network connections, or looking for emails. But here's the catch. Each one of these little processes is eating up 5 to 10 megabytes of memory space right off the bat. And to put that daily usage into perspective, think about the apps you actually want to use. A single modern user application nowadays, it takes about 500 megabytes of memory space just to start up. Because our computers only have a limited amount of main memory, or RAM, trying to keep all those background processes, plus our heavy apps, active all at once, well, that would require a massive, ridiculously expensive amount of RAM. Basically, our main memory gets completely overwhelmed before we've even typed a single word. So, how do we deal with these extreme memory overloads without making computers impossibly expensive? Operating systems use a couple of approaches, like virtual memory, but the absolute ultimate hero of our story today is swapping. Swapping is just this ingenious technique. Basically, when the main memory gets critically full, the memory manager steps in and temporarily moves or swaps out an idle or blocked process right over to the backing store, which is your hard disk. This clears up precious space, allowing a process that's actually ready to execute to be swapped into the main memory. It's literally a constant high-speed juggling act. And this juggling act relies on what we call priority-based preemptive scheduling. Imagine it like this. A low-priority process is running, right? But then it gets blocked, or suddenly a much higher priority task arrives on the scene. The memory manager instantly steps in, swaps out that lower priority process to the disk, and seamlessly swaps in the high priority one to the RAM so it can run immediately. When that high priority task is done, the lower priority one is just rolled right back in to pick up where it left off. Ideally, this whole swap-out, swap-in cycle happens so incredibly fast that your main memory is always purely filled with processes that are ready for immediate execution. Now, all this frantic moving around naturally brings up a really crucial technical question. When a process is swapped out to the disk and then comes back into the main memory later, does it go back to the exact same memory space it had before? Think about it like a person leaving their seat in a super crowded movie theater. When they come back with their popcorn, do they have to sit in that exact same chair? Well, the answer completely depends on a technique known as address binding. We essentially have two scenarios here. If the address binding is done statically, meaning it's permanently fixed during the compiling or loading phase, then relocating the process is incredibly difficult. It absolutely expects its old seat back. But thankfully, modern systems mostly use what's called execution time binding. This seamlessly allows a swapped-in process to be mapped to a brand new physical address the second it returns, because those physical addresses are actually computed right there on the fly during execution. It just scans the room and finds the new available seat. There is a tiny catch, though. When you have processes constantly swapping in and out of all these different locations, it inevitably leaves behind multiple fragmented gaps. We call these memory holes, and they get scattered all throughout the RAM. Now, you might be thinking, well, why not just push all the active processes downward to combine those holes into one big, clean block of free space? That's a technique called memory compaction. But actually doing this requires way too much CPU time. Your processor would be so busy constantly cleaning up and reorganizing the memory that it wouldn't have any time left to actually run your applications. So generally speaking, systems try to avoid this heavy compaction. All right, so far we've been looking at the main memory. But what's happening over on the hard disk, the backing storage? The disk obviously needs enough reserve space to hold all these swapped out process images. The operating system basically has two choices for how to handle this. It can create a separate swap file for every single swapped out process. The downside there? It creates tons of little files, which seriously slows down input and output search times. Alternatively, the OS can use a common swap file, which is just one massive single space on the disk. The challenge with that approach is that the total size of this common file has to be very carefully estimated right from the start because it strictly dictates how many processes can be swapped out at once. And that actually leads us right into another structural puzzle the operating system has to figure out on the fly. When a process is finally ready to jump back from the disk into the main memory, how does the system know exactly how much space to give it?
To solve this, the memory manager looks at the actual nature of the process itself. We have to contrast fixed-size processes with growing data segments. If a process is created with a fixed size that is absolutely never going to change, the OS simply hands over the exact amount of memory needed. No more, no less. But if a process has a data segment that's probably going to grow while it runs, the system intentionally grants it a little extra buffer space, right when swapping it in. It's a super smart move, honestly, because it completely avoids the heavy overhead of having to shift the process to an entirely new location later, just because it grew a tiny bit.
So, bringing it all together, what are the crucial takeaways from our explainer today? Swapping is an absolute lifesaver. It dynamically moves idle or blocked processes over to the disk, which ensures that your limited, precious RAM is strictly prioritized for processes that are actually ready to run. And it manages this entire circus through careful address binding and really smart memory allocation. It truly is the unsung hero keeping our PCs running smoothly. But it does leave us with a pretty interesting thought. As our applications and AI models become incredibly massive over these next few years, is traditional swapping going to be enough to keep up, or are we on the verge of needing a completely new way to manage computer memory? Let me know what you think. If you found this explainer helpful, please hit that subscribe button to join us here at the KognitoKey channel, and definitely like and share this explainer with your friends. Thank you so much for watching, and keep learning.